Hello all. So in the last class we completed the functioning of our partition algorithm that was expected to be used in quicksort. So what exactly our partition was doing is that partition was taking three arguments. One was the array A, then was the lower bound, or that was earlier called as low, and P as the upper bound of the array. Then it was just returning the exact position of mth element of the array in the form of j. Along with this, it was also setting the mth element at jth location or at its exact location. So this was the functioning of your partition algorithm that we studied earlier. Now let's discuss the time complexity of our partition algorithm. Time complexity. So the algorithm was working on the principle of just let there be the array denoted like this. The higher bound was p, the lower bound was m. So there was a pointer I that started from moving left to right. There was a pointer j that was moving from right to left, and we were just checking the crossing point of your I and j, and the point where I and j crosses was the point of swap in between your mth element and your jth element, or you can say that at that point j was pointing to the exact position of your mth element. This m was called as your pivot position. So this was the functioning of your partition algorithm. Now what should be its complexity? I think its complexity should be of the order of the number of elements present within the list, within array A, or you can also say that it may be equal to your p minus m. It may be of the order of your p minus m, isn't it? Because it is going to compare, or you can say it is going to run through the number of comparisons or the number of iterations which are just equal to the number of elements present within the array. So their complexity, or you can say the complexity of partition algorithm, will be of the order of number of elements present within the list. Okay, now let's move to the main quicksort algorithm, that is the quicksort algorithm. So the quicksort works on the principle of your divide and conquer approach, which says that if there are n number of elements, then we need to break or divide the problem into subparts. Let it there be p1, p2 up to pk, and we need to check are they smaller enough to be solved and to be able to return the solution back, so that all solutions may be recombined to form the final solution of your problem P. So this was the divide and conquer approach. So how it functions in case of your quicksort? So in the case of your quicksort, let there be n elements, or let there be suppose 8 elements saying 1 2 3 4 5, then 6, then 7, and then suppose 8. So let there be 8 elements. List containing 8 random elements was there. So we need to solve it, we need to sort it using our quick sort method. So quick sort functions just by making the initial call to our partition algorithm with argument 1 and 8. Means this is the, it has an index is equal to 1, it has 2, it has 3, 4, and so on. So it is the 8th index of the array A. Fine. So an initial call to your partition algorithm is made. So the what your partition algorithm will do is that it will consider this as your pivot element. Fine. And now it will try to try to find the exact location of your element A of 1, that is equal to 7. Means it will try to fix the 7 at its exact position. Along with this, that position J will also be returned. So this is going to be the function of your partition. So suppose this call was made and element number 7 got settled through the first call to partition. So where it is expected to be settled, let it be, because it is the list containing 1 to 8 elements. So the partition obviously is going to settle element number 7 at the 7th location. So let us assume that the output of your partition algorithm is such. Okay, fine. So element number 7 got settled here, and its exact position, it means the value of J that it returned is also equal to 7, means the index. Okay, so this is the value it is going to return. Now just try to observe that in the output of your partition, this element 7 is finally settled. In no way the position of this 7th element is going to change throughout the process. Okay, now observe that all the elements at the left are smaller than 7th element, and at the right are greater than 8. So this element number 7 is settled. Now just try to visualize the problem, or you can say in the repetitive behavior. Try to observe it like the iterative procedure, same procedure that was called initially. Or you can say that now 5, 2, 3, 1, 4, and 6 list is there, and the second list containing only element 8 was there. Done. So our problem is divided into 2 parts further, one containing single element, the other one containing 6 number of elements. Done. Now this list is again expected to be solved using the same algorithm, both of these. Okay, so in this case m is equal to 1 and your p is equal to 1, 2, 3, 4, 5, and 6. And in this case m is equal to 8 and p is also equal to 8. And we know that list containing single element is always sorted, so no further calls will be made to solve the right list. Done. Now this list is again to be sorted using the same algorithm. It means we need to call partition again with m is equal to 1 and p is equal to 6, this one. It means now we need to find the exact location of the first element, this one, which is equal to 5. Fine. So it will act as your pivot element now. Done. Now if partition is called using these two arguments, then we know that the exact location of 5 is 5th in the list. Fine. So let us the resulted list be 2, 1, 3, 4, 5, and 6. So this 5 got settled. Done. 5 got settled. So this is the second element to get settled. Seventh element of the list was settled here. This is the fifth element to got settled, and third one was also there. Fine. Eighth element was also settled. Done. Now observe this. Again there are two lists made. One is from M to J minus 1. This will be returned as J, na? And second one is J plus 1 to P. Isn't it? So two lists are there, and we know that a right list contains only 6 as a single element. So it is sorted. It means it will be fixed at location 6th. Done. Now the left list is 2, 1, 3 and 4. Fine. So again the partition will be called with this. When partition is called, it will be called using M is equal to 1 and P is equal to 4. So 2 will act as the pivot element. Now its position will be settled down, means let it be the 1, 2, 3 and 4. So this is the exact position, or this is the J which is to be returned. Again two lists are there. Left list is already sorted, no need to do anything. The right list contains 3 and 4. So 3 and 4, again partition will be called. Done. Partition, when partition is called, 3 will get settled. Done. Its right list will be containing 4. It is also assumed to be settled. Done. So in this way, each call to your partition, each call to partition is settling out, is settling one element at its exact position. Done. So this is the simple logic of your partition algorithm, and along with your quick sort, this functions by making the initial call to partition. Partition just returns J. So jth element got settled. Two lists are there. So two lists are there. So let it be the list of n elements. Done. Initial call to partition was made. So partition returned J. Done. Let this be the J. So jth element got settled. Two lists are there. One is having size from M to J minus 1. Second one is having size from J plus 1 to P, assuming that it was starting from M and ending at P. Is it fine? So two lists are there. Again, partition will be called on this list, M to J minus 1 and J plus 1 to P. So these are the two lists. Partition will be called on this list. Partition will be called on this list also. So this call to partition will also settle one of the point, or you can say one of the element, that is, let it be the settled element which is equal to J. So again there will be two parts. One list will be this, one list will be this, and in the same way it is also going to fix a single element at this position. Two lists are to be made. These are the two lists upon which the partition algorithm will be called again. In this way, as the tree proceeds towards the bottom, elements got settled. Fun. So let us assume that initially we were at the root. So two calls were there at the most. So initial at this level, partition call settled one element. Done. So two calls are made to partition at this level. So at most two elements got settled here, and at its lower level, four calls were made to your partition. So at most four elements got settled in the second level. This just proceeds till the last level, or till your all elements n got settled. So this is the simple procedure, simple functioning of your quicksort algorithm. Okay, now let's move further. Now we have already observed the sorting using quicksort. Conceptually we have seen this. So the only difference between your quick sort and merge sort is that in case of merge sort, your problem of having n size was divided into two sub problems, each having size n upon 2 n upon 2. But in your quick sort, this division is just not defined, is just not fixed. Means the list may or may not be divided into n upon 2 each. It may be divided into let it be suppose 6. Let there are 6 elements in the your left list, then your right list is going to contain how many elements? N minus 7. Why n minus 7? Because the initial call to this partition, the initial call to the quick sort or initial call to partition will be settling one element. Done. So the list containing n minus 1 elements is remain there to get sorted. So the n minus 1 elements were broken in two parts. One was from 1 to j minus 1, second was from j plus 1 to n, and if we sum up both these, then they return up to n minus 1 elements. So what my purpose is just to convince you that in case of quick sort, the division is not uniform. Fine. While in case of merge sort, this division was fixed, that at every step the list or the problem was supposed to be divided into two equal halves. Fine. Now we already know the solution method for your quick sort, or all in all, if we see any divide and conquer approach, then it was involving three parts: divide, then solve or conquer, then recombine. Fine. Now we know that recombination is not required at all. Why it was not required? Because at this initial call, first element was settled. Fine. Means one element was settled, not exactly first, one element was settled. One was settled at its 6x position. Now let us two further call to partitions were there. So two elements will be settled here, will be settled, and further if two calls to each partition were resulted at the lower level, then 4 will be settled here. Done. In this way your n elements will be settled, and we do not need any recombination of the solutions. Done. Because we already know that an array is always passed by reference, and the changes which your partition algorithm is going to make are to be reflected in the global list. Fine. So there is no need to any recombination at all. Now there are only two parts, one is divide, one is solve. Now this solution was resulted using your partition algorithm that we already discussed. Now we'll learn how to divide, how this division takes place. Now let us try to write the algorithm for your quick sort. Let it name as quick sort. Two arguments are passed to it, one is low and one is high. Now we already know that every sorting algorithm functions if and only if your low is less than your high, or you can say if the problem is smaller enough. Fine. And if it is not smaller enough, then we need to just divide it. Now this division is going to take place at a point which is termed as your j. Now j is the output of your partition algorithm when we make a call to partition with two arguments, that is low and high. Fine. Now this was the list. Done. This was low, this was high, suppose. Now it was containing your n elements. A call to partition was made. Partition returned your j, means it returned that your pivot element or this one element, the first element, was actually belonging to jth position. Jth was its exact position. So this was the j returned here. Now there are two lists. One is from low to j minus 1. This is your j minus 1 and this is your j plus 1. J plus 1 to high. And this is low to j minus 1. So two further recursive calls are to be made to the same algorithm, that is quick sort. So the first call will be from low to j minus 1. Fine. And the second recursive call will be for j plus 1 to high. Isn't it? Now this call will further be calling your partition internally, and this will also be calling your partition algorithm. It means this left list again will be called with the same algorithm. This again will be called with the same algorithm. So that this will further be divided by finding the exact position of your pivot. This again will be further recalled by finding your exact position of your pivot element. So these were the pivot elements of these two individual lists. So this is the algorithm for your quick sort. Okay. Now let us try to discuss its time complexity. Means the time complexity of your quick sort. Quick sort. Now let us try to have a case when the list is already sorted. Means to say, let our list contains 2, 4, 6, 8, 10 and 12 as its elements. Now try to observe the behavior of your quick sort. Means this is the list. So in this case, low is equal to 1 and high is equal to 1, 2, 3, 4, 5, 6. High is equal to 6. So quick sort will be called with arguments 1 and 6. So 1 is greater than 6 will be checked, which is true. It means the problem will be divided and there will be a call to partition with 1 and 6 as arguments. The result is expected to return into your variable j. Done. So it means we need to fix this element, first element, as our pivot element. Means pivot is the one whose exact position is going to be found. So we need to find the exact location of your pivot element, and it will be done using our partition. So how partition works for this case? So from left to right there will be a pointer I, from right to left there will be a pointer j, isn't it? So left to right pointer I will be searching for an element which is larger than 2. So it is expected to stop here, isn't it? And from right to left j will be varied in search of an element which is lesser than or equal to the pivot element. So this is not lesser than equal to, this is not, this is not, this is not, this is not, and this is where the j will stop, because 2 is equal to 2. So j will stop at 1 and I will stop at 2. So we are going to check whether I is less than equal to less than j or not. Done. This condition is false. That's why there will be no swap between a of I and a of j, but there will be a swap between a of j and a of m. Done. Because m was itself lying at this position. So pivot element is expected to be swapped, to be exchanged with itself. Or you can say because 2 was lying at its exact position, so nothing will be swapped at all. Done. So it will remain at its exact position, which is equal to 2. Fine. And the number of comparisons which were made in finding this is equal to n. Done. In settling down your element number 2. Now the problem is divided into two parts. One is containing your left list, which is the left part of 2, means this one, which is the nil one, and one is your right list. So the right list will be containing 4, 6, 8, 10 and 12. Done. So there is no way, or you can say no benefit of calling recursively for a list which is containing zero number of elements, isn't it? So we are going to make a recursive call your to your quick sort with this list. If this is the list, it means this is the pivot element. We need to fix its position, and if we just wish to again trace it in the same way as its parent, then this 4 is expected to just stay here. Done. And how many number of comparisons it will require? N minus 1. So this 4 is fixed, means left list is of size nil, right list is of size, or you can say will contain 6, 8, 10 and 12. Done. So this time again this 6 will act as pivot element and it is at its exact position, so it will be fixed here. Again left list will be nil and the right list will be 8, 10 and 12. And how many comparisons it took? N minus 2. And how many comparisons it's going to expect is your N minus 3 up to 1 when 1 doesn't reach. Now just try to sum up the values which are the number of comparisons taken was equal to n, then n minus 1, then n minus 2, then n minus 3 up to 1, or you can say that 1 plus 2 plus 3 plus 4 up to n. This is the number of comparisons required to sort the given list. If we sum this AP, means arithmetic progression, then it will going to be of the order of n square. So we can say whenever our list is sorted in the desired order, then its complexity will be of the order of big of n square. This also counts as the worst case of our quick sort. Now we'll also see further that it doesn't matter in which order the list is sorted, desired one or the opposite ones. In both the cases, the complexity is going to be of the order of n square. The only point is in conclusion that if the list is sorted, if the list is already sorted, then the quick sort is going to behave in the worst case, which is going to take the time that is big O of n square. Okay. Now let us look at the case when the list was sorted in the reverse order, or you can say when the list was 8, 5, 4, 3 and 1. Suppose this was the case. So initial call was made using this list. Done. Now when partition functions on this, it tries to find out the position of the pivot element which was equal to 8. Fine. So I starts moving from here, J starts moving from here. Done. Now from left to right, we are going to search for the element which is larger than the pivot element. So larger is not found, or you can say the search stops at J plus 1, 1, 2, 3, 4, 5, or you can say I becomes equal to 6 and stops because the list ends there, while J moves from your 6 towards left in search of element which is lesser than or equal to your pivot element. Done. Now the first one which is equal to 1 is the end of search for your first go, means 1 is lesser than 8. Done. So these two elements will be what? These two elements will be exchanged. Yes, no? These two elements will be exchanged. Let us try to look more deeply that at this location, at this position, the value of J is equal to 6 or you can say 5. The value of J is equal to 5. The value of I is equal to 6, but I is not less than J. It means there will be no swap between A of I and A of J. Fine, but there will be a swap between your A of J and pivot element. Done. It means we need to swap your pivot element and your jth element. So the list becomes 1, 5, 4, 3 and 8. So this is the exact position of your pivot element. Fine. It means it is expected to break into two parts. One is the right part containing nil elements, one is the left part containing 1, 5, 4 and 3. Isn't it? 1, 5, 4 and 3. Yes, no? So this is 1, 5, 4 and 3. So in this list your pivot element is this one. Okay, so I will move from left to right and J will move from right to left. So while moving left to right, I will stop at equal to 2 while J will start from 4. Fine. So when J will start from 4, it will stop at, because this 3 is not less than 1, 4 is not less than 1, 5 is not less than 1 and 1 is equal to 1. So J is going to stop at equal to 1. So these cases also will compare if I is less than J, which is not. It means we need to swap our A of J and pivot which are both equal to 1. It means no swap is going to be there. So 1 is assumed to be at its exact position. And in how many number of comparisons? That was equal to n minus 1. And how many its parent consumed was n. Fine. So at this level, two lists will be there. The left list will be containing nil elements because there is nothing in the left of 1. The right list will be containing 3 elements, 5, 4 and 3. Done. Again 5, 4 and 3. The pivot element is here 5. Done. So I will start from here, J will start from here. So if we just repeat the process, then these two will be exchanged. Done. So your list will be 3, 4 and 5. So this is the exact position of 5 in your n minus 2 number of comparisons. Two lists will be there. One is the right one containing nil number of elements. The left one will be containing 3 and 4 as its element. So again 3 is the pivot element. It will start sorting. Then again there will be two lists. One is containing nil and other one containing one element. So this process just reiterates till last element, or you can say the last element of the list got settled. If we just observe the number of comparisons it took, means it started from n, then n minus 1, then n minus 2 till 1. It means again the same AP starting from 1 to 2 to 3 up to n is going to be formed. Fine. It summed up to some expression that is proportional to n square, or we can say that the complexity of this case also is of the order of n square, which is the worst case. So all in all, we can say that if the list is sorted, then it doesn't matter whether it was in the desired order or it was in the opposite order. Quick sort is always going to consume the time which is of the order of big of n square, and this is termed as the worst case of your quick sort. Okay, now let us move to the other cases, means the best case and the average case. One thing to know that is that quick sort is having no best case at all. So at the best it can perform with its average case complexity, which we are going to just derive, and the worst case complexity I've already derived, that is equal to of the order of n square. Now we need to look at the average case complexity. Average case complexity of your quick sort. So this is going to be our next task. So before studying, or before going to derive the equation, we need to assume certain things. So there are two assumptions. Assumption number 1 is that each element is unique in the list. It means there is no duplicacy of the elements. And the second important assumption is that the probability of each element becoming the ith smallest element is equal, means to say that after each call, after, or you can say after, let us assume after the first call to your partition algorithm, first element, second element, third element, and your nth element of the list has equal probability of becoming the first smallest element and the second smallest element and the third smallest element and the nth smallest element. And what exactly is that probability? That is equal to 1 upon n, means by 1 upon n probability, the element number 1 may be the first smallest, element number 2 may be the first smallest, element number 3 may be the first smallest. So the probability of becoming the ith smallest element is equal, which is equal to 1 upon n. So these are the two assumptions for this. Now move towards writing the recurrence for average case. Now before writing the recurrence, let us take a case that 1, 3, 2, 4 and 5 were the 5 elements upon which the call to partition was made. Fine. And partition returned the exact position of pivot element, done, as equal to j. So this position definitely will be going to be third. Fine. So this is going to be its exact position, let it be j, done. So two lists further will be made, one is the left one, other one is the right one. Now how many elements are expected to be there in the left list? It is equal to how many? It is equal to j minus 1 elements. And how many elements are there in the right list? It is equal to n minus j, as n is equal to 5 in this case. So your left list, and j is equal to 3. So your left list will be containing 3 minus 1 is equal to 2 elements, isn't it? And your right list will be containing 5 minus 3 is equal to 2 elements, isn't it? So after every call to partition, there will be the one element which is going to be settled, which is equal to at jth position. Fine. Two lists are going to be there. One is of size j minus 1, the other one of size n minus j. Now assume, now try to replace this j with k. So there will be two lists, one containing size k minus 1 and the other one is going to contain n minus k number of elements. So this is going to become the basis of our average case. Now as we know that elements are having equal probability of becoming ith smallest element, so assume that the first call returned k. Fine. First call to the partition, first call to your partition algorithm with n random numbers returned as k. Now we know that this k may be 1, this may be 2, this may be 3, this may be 4, this may be n. Fine. It means the pivot element may be the first smallest element, maybe the second smallest element, maybe the third smallest element, maybe the fourth, maybe the nth. With how much probability? With probability 1 upon n. Done. So what exactly we are going to look at the average cases, that will be assuming that this k was equal to first, this k was equal to second, this k was equal to, or you can say the position returned was third, was fourth, was nth. We are going to consider the time taken by all these n cases, and once we found that time, we are going to divide that time by n. So it is going to generate the average case time complexity of our quicksort. Fine. So we know that there are two lists two lists are going to be generated after the partition returned k. One list will be of size k minus 1, the other will be of size n minus k. Fine. So let us assume that c of a of n denotes the average time taken for the quick sort having n elements. Done. So it will be the sum of the average time taken for sorting this list, done, plus average time taken for sorting this list. Fine. And now we are assuming that this k may be 1, this k may be 2, this k may be 3 and this k may be n. So we are going to sum this list from starting of k from 1 to n. Done. So we are going to find its average, and for finding its average we need to just divide this whole term by n, isn't it? So this is the time taken for the first list, this is the time taken for the second list, this one. Now this k may be 1, this k may be 2, this k may be 3, this k may be n. So we just added that all. Fine. We obtained the sum, and for finding average we need to divide it by the number of elements present within the list. Done. So this is all recursive part. Now if we observe, just we try to recall the time taken by any of the divide and conquer approach, then there was a recursive part plus there was f of n. So this 2 denotes the recursive part. Now what is the value of this f of n? Now just try to recall the algorithm for your quick sort. So this was the algorithm for your quick sort. What exactly it says is that if your list is containing more than one elements, then you need to make a call to partition first. Done. And this call to partition is going to take your n plus 1 number of comparisons. Only then a value of j will be returned. Now with that value of j, first recursive call to the same algorithm with low to j minus 1 as arguments will be made. Second call with j plus 1 to high will be made. So this n plus 1 is also required to be there, or it is going to act as your f of n. Fine. So we need to add this term in the recursive equation for average time complexity. So we need to add this n plus 1, which accounts for the first call to partition. So this is the time taken for the first call to partition. Now just try to multiply both sides of this equation with n. So it will become n Ca of n will be equal to n into n plus 1 plus n will get cancelled, 1 less than k less than n, then Ca of k minus 1 plus Ca of n minus 1. Now try to evaluate these terms. So what it says is that n into n plus 1 will remain the same, plus now put the value of k is equal to 1. If k is equal to 1, then it will becoming Ca of 0 plus Ca of n minus 1, isn't it? Done. Now put the value of k is equal to 2. So in that case Ca of how much? 2 minus 1 is equal to 1 plus Ca of n minus 2 will be there, isn't it? Now if you put the k is equal to 3, then it will be Ca of 2 plus Ca of n minus 3. Now pick up the last end. If we put the value of k is equal to n, then it will become Ca of how much? N minus 1 plus Ca of 0. Now if we put k is equal to n minus 1, then Ca of how much? N minus 2 plus Ca of 1. Now just try to observe this behavior. Just try to observe, and if we try to simplify, then we can write this equation can be written, means this term will remain the same, plus CA of 0 here, CA of A 0 here, so 2 times, CA of n minus 1 here, CA of n minus 1 here, 2 times, C of 1, C of 1, C of n minus 2, C of n minus 2, means to say if we just take 2 common, then we can write that CA of 0, then CA of 1, then up to CA of n minus 1 is going to be its exact simplification. So name it as equation number 1. Fine. Is that okay with all? Yes, no? Okay. Now name this equation as equation number 1 and name this equation as equation number 2. Fine. Is it okay? Now try to rewrite what we attained till yet is that the value of n multiplied by CA of n is going to be equal to n into n plus 1 plus 2 of CA of 0 plus CA of 1 plus up to CA of n minus 1. So this is the equation number 2. Now just observe the number of comparisons taken by your quick sort when the value of n was equal to 0, when the value of n was equal to 0 and when the value of n was equal to 1. How many number of comparisons will it take? It means when the number of elements or no element was present in the list, then the time taken by quick sort will be equal to 0, means number of comparisons is equal to 0. Number of element comparisons. What is this? Is element comparisons. Element comparisons. And when even n was equal to 1, then also number of elements comparison was equal to 0, because this condition, this one, if condition will be false, will be true, will be false, and it will not go further, it will just return back. So these two values are CA of 0 and CA of 1. So in the later case out here, we can say that CA of 0 equal to CA of 1 is equal to 0. So these both are true, or you can say that n of CA of n may be written as equal to n into n plus 1 plus 2 of how much? CA of 2 plus CA of 3 plus CA of n minus 1. So this is to be very exact our equation number 2. This is our equation number 2. Fine. Now try to replace n with n minus 1 in equation number 1. What was the equation number 1? So this was the equation number 1. This one. This is the equation number 1. If we try to replace n by n minus 1, then it will become n minus 1 into CA of n minus 1 will be equal to how much? How much? This n will become n minus 1, n minus 1 plus 1 out here. So this will be n minus 1, this again will be n minus 1, and for 1 k n minus 1, and it will be CA of k minus 1 plus CA of n minus 1 minus k, isn't it? So this is going to be your new equation. Now try to solve it also. So it will be equal to n into n minus 1 and along with 1 upon n minus 1, isn't it? Yes, no? That was missing from here, no? Or okay, that was actually just that was just cancelled out, so no need of writing this. So it will be equal to this. Now try to simplify this. Okay, now put the value equal to k is equal to 1. So in that case, Ca of 0, so it will be equal to Ca of 0 plus Ca of, because k is equal to 1 now, because k is equal to 1, so it will become Ca of n minus 2 plus, now put k is equal to 2. So in that case, Ca of how much? 1 plus Ca of how much? N minus 3, isn't it? Plus now put k is equal to 3. So Ca of 2 plus Ca of n minus 4. Fine. Now start from the last end, that is k is equal to n minus 1. So it means Ca of, if we put k is equal to n minus 1, then it will become Ca of n minus 2. This term will become Ca of n minus 2 plus Ca of how much? N minus 1 minus n minus 1 further. इसको थोड़ा और रिजॉल्व करें, then what will be, it will become n will get cancelled, isn't it? So it will become equal to 0. Done. So it will be Ca of 0. If we put k is equal to n minus 2, then the term will be Ca of how much? Ca of n minus 3 plus Ca of 1. Just try to evaluate it. Now try to look at this as a whole. Means Ca of 0 is there, Ca of 0 is there, then Ca of n minus 2, Ca of n minus 2, then Ca of n minus 3, Ca of n minus 3, Ca of 1, Ca of 1. It means we can just write this equation as equal to n into n minus 1 plus 2 into Ca of 0 plus Ca of 1 कब तक plus Ca of n minus 2, isn't it? Ca of n minus 2. This is your equation number 3. Let us. So Ca of 0, Ca of 1, both are 0. So it will again start from Ca of 2. Done. So your equation number 3 will be n minus 1 into Ca of n minus 1 will be equal to n into n minus 1 plus 2 of Ca of 2 plus Ca of n minus 2. So this is equation number 3, to be very exact. Fine. So this is equation number 3 and this is equation number 2. Now the next step is just subtract equation number 3 from equation number 2. What we'll get? We'll get n into Ca of n minus n minus 1 Ca of n minus 1 will be equal to, now try to observe this is equation number 2. So n into n plus 1, so n into n plus 1 minus this term n into n minus 1, fine, plus your this term, the second part, this one, from Ca of 2 to Ca of n minus 1, and what exactly this 2 of Ca of 2 to Ca of n minus 2. So Ca of 2 to Ca of n minus 2, these all terms are also lying there in equation number 2. There is only one extra term in equation number 2, which is Ca of n minus 1. So it will only remain, others will cancel out. So the solution of this part when negated from the same part in the equation number 2 is 2 of Ca of n minus 1, because this is the only term which is going to remain, others will be cancelled out. So this is our result. Done. Now try to simplify this. n of Ca of n minus n minus 1 CA of n minus 1 will be equal to your n square plus n minus n square plus n plus 2 of CA of n minus 1 is equal to n square will cancel out, 2n plus 2 of CA of n minus 1, isn't it? Done. Now just keep it at the left side, n of CA of n, and bring it on the right side, so it will become plus n minus 1 CA of n minus 1. Done. It will be equal to 2n plus, take this as common, CA of n minus 1 common, then it will be 2 plus n minus 1, so it will be equal to 2 of n plus CA of n minus 1 multiplied by n plus 1. Done. So n CA of n is equal to this. Now just keep CA of n at the left, and the right side will become 2 because n upon n will be cancelled out, and CA of n minus 1, okay, multiplied by n plus 1 upon n will be there. Done. Now just divide both sides by n plus 1, so CA of n upon n plus 1 will be equal to, now divide this term by n plus 1, so it will become CA of n minus 1 upon n. Now divide this term by n plus 1 plus 2 upon n plus 1. So this is the final recurrence relation in the simplified way. Name it as equation number 4. So this is required to be taken up for further simplification. Okay, now just rewrite the equation expression that we just achieved, that is equal to CA of n plus 1, CA of n, CA of n upon n plus 1 is equal to CA of n minus 1 upon n plus 2 upon n plus 1. So this is the expression that is to be taken further. Now in this expression, try to put the value of this, recursive part. Okay, for putting the value of this recursive part, we just need to replace n by n minus 1 in this whole equation. Try to replace n by n minus 1. Whatever you get, just put it here. Okay, so what exactly we are going to obtain is CA of n minus 2 upon n minus 1 plus 2 upon n is going to be the value of this, plus 2 upon n plus 1 was the earlier value. Now try to put this value, put the value of this expression using your equation number 4 again, this one. Now for doing this, we need to replace by n by n minus 2. Fine. If we do this, then what we get is CA of n minus 3 upon n minus 2 plus 2 upon n minus 1. Okay, 2 upon n plus 2 upon n plus 1 were our earlier parts. Just try to proceed in this way. Now assume that this term becomes your 2 upon 3. Assume that just by starting 2 n plus 1, 2 upon n plus 2 upon n minus 1 plus it ended at 2 upon 3. If it is 3 out here, just observe, if it is n minus 1, then 2 lesser will become your C of A, means C of A will be 3 minus 2 is equal to 1. देखो ना, यहाँ पर n minus 1 है तो यहाँ पर कितना n minus 3 है, तो if यहाँ पर C of 3 है तो यहाँ पर कितना होना, सी ऑफ 1 होना है, isn't it? यहाँ पर n-1 है तो यहाँ पर n-2 है, इसका मतलब यहाँ पर 3 है तो यहाँ पर कितना होना है, 2, isn't it? Done? So we just try to generalize it. Now we know that this term is equal to 0, so it will become 2 upon 3 plus 2 upon 4 plus up to 2 upon n plus 1. This is going to be the equation. Now just by taking 2 as common and then by just summing it up, summing it from k, where k is less than equal to 3, greater than equal to 3 and less than equal to n plus 1, so it is the sum of 1 upon k, isn't it? Done. Now we can just replace this value by an integration which starts from 2 and ends at n plus 1 and which is equal to 1 upon x of d of x. Can we do this? It is going to be lesser than or equal to this. Why? Because it is starting from 2 and ending at n plus 1, while your summation was starting from 3 and was ending at your n plus 1. Along with this, 2 will remain the same. 2 will remain the same. Okay, is it fine? It is going to be lesser than or equal to this integral term. Now if we try to solve it, then it is going to have a solution which is equal to log of n plus 1 minus log of 2 base e. So assume, fine, and it is multiplied by 2 further, this one. So just by considering this sign, we can write just that Ca of n upon n plus 1 will be going to be lesser than or equal to 2 into log of n plus 1 minus log of 2. Done. Or we can say that Ca of n will be lesser than or equal to 2 into n plus 1 multiplied by log of n plus 1 minus log 2. Now this is your expression, name it as f of n. Very easily you can prove that this expression will be having complexity which is of the order of n log of n. Just apply your any of your asymptotic notations, any of your asymptotic definition. That may be theta, that may be big omega, that may be your small omega with certain changes. So in this case, because we are assuming that this term is going to be lesser than or equal to this one, so the definition of your big omega fits here, and we can say that its complexity is of the order of this with some suitable values of c and n naught. So we can say that the complexity, or you can say the average case complexity, or you can also say that best case also, because there is no actual best case of quicksort. Best case complexity of quicksort will be of the order of n log of n, while the worst case complexity of quicksort is of the order of big of n square. So this is the complexity analysis of your quicksort. Thank you.